Professor Gui. And Professor Gui actually get his bachelor degree from in 2005 from Zhejiang University. And after that, he furthered his study as a PhD in the same university in the major of engineering thermal physics. And after that, he worked as a associate professor in China University of Petroleum, Beijing. And after in 2015, he go to Tsinghua University as an associate professor. And now he is a director of the Institute of Nuclear and New Energy Technology at Tsinghua University. In his freelance areas, he has many publications, and he have two books published in Elsevier and Springer in the multi-phase floors. And also he has publications in the journal of some very good journals, for example, the Power Technology and the International Journal of Heat and Matter Transfer and the Chemical Engineering Science, and so on. And today we are very happy to invite Professor Gui Lan give us a presentation. The topic is a GPU-DEM model for the pipe flow and heat transfer studies in HTRG-packed bed. Okay, welcome Professor Gui Lan, give us presentation.
Okay, thank you, Professor Yao, and thank you for the chair to give me an opportunity to have a presentation. Now my topic. Can you see the screen?
Yes, we can see it. Yeah, your voice is also very good.
Okay. I will try to. Okay, the title of my presentation is a GPU-DEM simulation for the industrial scale pebble flow and heat transfer in high temperature gas-cooled reactors. I'm Gui Lan. So this is me, and the Professor Yao has introduced me a lot, and I'd like to show another person. This is Dr. Zhou Chen. He is my PhD student. And today I will show most of his research on the GPU-DEM simulation on the industrial scale pebble flow in HTGR. So my presentation basically has four parts: the background, the pebble flow in HTGR, the heat transfer in HTGR, and the conclusion. Let's go to the first part. Basically, I would to give a brief introduction about the HTGR because I think most of you not in the community of nuclear energy. So HTGR means the high temperature gas cooled reactor. You may know in the nuclear engineering, the most mainstream reactors are pressurized water reactor. It uses water as a neutron moderator and also coolant. But in high temperature gas cooled reactor, he uses helium gas as a coolant to transport the heat generated by the nuclear fission reactors. And the few about in the reactor is composed of a number of pebbles. It's a very large spherical shaped and made by graphene materials. And this is a picture about the few pebbles. And it has some nuclear fission, nuclear particle. And its few particles diameter is about 1 millimeter. And about 20,000 such kind of small small particles will build a large pebble. This diameter is about 60 millimeter. So in the reactor core, it's composed of a number of such kind of sphere pebbles. we can regard it as just as spherical rocks, and the heating gas will go through the pebble bed and remove the heat generated by the pebbles. So over the world, there are two pebble HTGR reactors. The first is HTGR-10. Its power is 10,000 thousand megawatt, 10 megawatts. Okay, and this is another HTGR. It is always it is already in commercial operation in Shandong province of China, and these two kinds of nuclear reactor was all were developed by the Institute of Nuclear and New Energy Technology by Tsinghua University. And this is a size comparison about the two reactors. Okay, now my research task is want to simulate what will happen in the reactor course. It's composed of 420,000 pebbles, and we need to know where the pebbles are located and where it come from and where it will go, and I want to how the heat transfer between the pebbles and between the heating gas pebbles. Oh, then I will give you overview about the research about how to modeling the pebble flow and the simulation. About 80 years ago, one of my PhD students, Dr. Wu, has built three simple radiation models. He used the Voronoi cells to cover all the pebbles inside the bed, and compute all the view factors for each pebble to each surface of the Voronoi cell. And he has a very analytical expression for the view factors, and give the heat flux, radiation heat flux by a simple expression. And then he just used the CFD-DM coupled method to calculate the heat transfer between the heating gas and the pebbles, and also the heat transfer of conductive and radiation between the pebbles. And then he also, because the pebbles is very large, so if we use the CFD-DM method, we find the flow field for heating gas is very it uses very coarse meshes, so we do not have get enough information about the heating gas flow. So we needed to use more. We needed to use finer mesh grid. So we just use just propose a smooth volume fraction model. And basically, if we use the mesh grids smaller than the pebbles size, now we will calculate each the volume fraction in each cell. So, for example, in when the cell is within the particle, its volume fraction is zero, and it is outside the particle, its volume fraction is 1. So there is a sharper transition between the inside and outside region. So it may be introduce some numerical instability when you use CFD-DM simulation. So we just try to use smoothing concept, the concept of smoothing volume fraction. We use the equation of the thermal equation diffusion. We can regard the W as particles mass, and let it diffuse to a locally region. And we use expression to analytical expression to calculate the mass of particle in each cell, and calculate. Then we can calculate the volume fraction in each cell, and this kind of distribution of volume fraction would be very smoothing, and it's a benefit for nuclear simulation stability. So this method has has three basic advantages. First, it is smoothing. Then it is local. I mean, and then it is conservative. Conservative means it does not introduce additional volume fraction or some additional force within the two-phase interaction. So we use this kind of method to simulate the spout, the bed, and also the pebble bed. But basically, I need to say frankly that this method has some shortcomings because it uses some fake or some unreal volume fraction. Although it is conservative, within a locally domain, but we cannot know we do not know which kind of what the degree of smoothing is the best or is real for each case. So it is still a fundamental issue we need to solve. Okay. Then after these models, we just want to use these models for real scale reactors. So the Dr. Zhou, you write the GPU-DEM code and embed all these models into his code and simulate speed up. Firstly, he speed up the view factor calculating by neural network method, and use this method to simulate the HTGR 10 reactor, and then extend it to a larger scale HTGR 200 reactor. And this is the picture of simulation results carried out by him. Basically, there's two approaches using the GPU-DEM. The first is using the NVIDIA graphic cards and use the CUDA program. The other kind approach is using OpenCL. We use the first, and this table lists the number of GPU-DEM workers, and also this table lists a number of researchers where which they compare the performance of one GPU versus one CPU, and this is our study, and we simulated about from 1,000 to 1,000,000 particles, and we find the overall speed up ratio ranging from 20 to about 400. And if the CPU time for each time step is for 12 cores of CPU needs about 140 million microseconds. But for GPU with RTX 30 and 3090, it's less than 4 microseconds, and it can be finished within 12 hours. But if you use CPU, it needs 12 days. So it is not applicable or acceptable for engineering application when we use CPU. So we must try to solve this to develop a GPU-DEM method. And this table compares the performance of GPU generations from you can see from one generation to the next generation, the overall performance may increase over than 100%. So it's a very promising method, and then we tried to use such a kind of method in our study. Okay, Second part is about using the GPU-DEM method for pebble flow in HTGR. The first is the DM. I think most of you know are very familiar about the DM. So I'd like to go through the DM method first. And this is the governing equations. And this is the parameters. And we use the Hertz-Mindering model for particle-particle contact. And for particle whorl contact, because the pebble beds for the pebbles and the whorls are made up of the same material. It uses graphing, so we just treat the whorls as large pebbles of infinite radius and treat the particle whorl interaction simply. This is the main architecture about the GPU-DEM solution. So it increase mainly divided into two parts: the host and the device. And for each program, we just yeah, compare we just use the CPU to solve the main stream and use the device part to solve the iteration. For particle collision detection, I think the locally searching algorithm or the neighbors searching algorithm is frequently used in DM simulation to simulation to save the computational cost. But if you apply this algorithm in GPU, we need to some specific treatment. Here is a sketch about how to use this algorithm. We just label all the particles and use a mesh to cover all the labels. And we use when we use this table, we know what's the label for each particle. So it will save the computational cost greatly. And for technical application, we use a unified memory addressing technique. We need to let the CPU and the GPU to read and write same data to avoid some confliction between the data transportation. And we also use two sets of data to alternately use each one to read and each one for writing. Then we can simplify the process of I/O. And these are technical details. And after we finish the coding, we need to verify if it is correct. So we just test the particle-particle collision by with a very small velocity and a very large velocity. We find that when we use different time steps, the relative error will change largely. So we find that if we use about about 10 microseconds, the relative error is reaching about 1%. So it's enough for our simulation. And we use experiment. This experiment was carried out by another group in Tsinghua University. So it uses hops and lets the particles inside the hops to flow outside the hop when the hop is lifting slowly. So the particles will piled up over ground, and we check the simulation results. The angle of the pose of the pebbles, and we find the consistency between the simulation and experiment very well. So the angle of the pose is ranging from about 20 degree to 30 degree when we use different kinds of sliding friction coefficients. Then after the code has been verified, we use this code to simulate the real reactor of HTR-10, and this is the parameter we use, and we simulated about 35,000 particles and get the three-dimensional data about the pebble flow inside the reactor core. And we also compare the performance, the accuracy when we use the CPU or we use the GPU, and we find that the results are almost consistent with each other. The relative error is very small. And also we compare the computational efficiency, and we can find if we simulate the large different kinds of particles, and we compare the average iteration the speed up ratio. We find if for example we use 1,000,000 particles, the speed up ratio may be reach as high as 20 for pebble flow. And this is another case about we use the same code to simulate the largest industry scale of pebble bed. We can see when the pebbles are loaded from the top of the bed one by one and discharged from the bottom of the bed, and we can this picture is will show us the top of the data of particles when we flow from the top of the bed, and this picture shows some when we use different kinds of loading method, so we can predict what is happening in the inside the reactor core. And we can use different kind of mixing index to see what's the level of mixing inside the bed, because the bed is composed of two kinds of pebbles. One is the pebbles with nuclear fuels, and the other is just graphene pebbles, just used as a moderator. So we need to know what's the mixing level between the two kinds of pebbles to see if the heat generation inside the pebbles is uniform or not. Also, we use different kind of friction coefficient to see what will the effect the coefficient friction coefficient affects the pebble flow inside the bed. So we find it except for the when we use the 1.3 as the friction coefficient, the pebbles may have some may have a final flow pattern within the final flow pattern. Other kinds, the mass flow is very uniform inside the bed. So we checked the real friction coefficient of the pebbles, and to give a very good prediction on the uniformity inside the pebble. Also, we can choose another very large initial angular velocity, because we need to know if the pebbles go into the bed with initial angular velocity, or how will it affect the pebbles location, its impact, and how will it affect the mixing level inside the bed. So we just use different kinds of initial angular velocity, and we find that the angular velocity has very few effect on the pebble flow, because its location is very concentrated into within a very small region, except we use a extremely large initial angular velocity to 1,000 radian per second. Its distribution may be scattered to a larger region. So, but we think it's not it cannot happen in real reactor. So we think it's not it will not does not affect the pebble flow inside the real pebble bed. Also, we just use the program to simulate different kinds of pebbles diameter. We use about 40 millimeter to 80 millimeter, and to see which kind of pebble diameter is best for the pebble flow inside. In actual reactors, it uses 60 millimeter. So we can verify its applicable. It can be used for real reactors. And the third part is of heat transfer inside the bed. This is a governing equation for each pebble, and the heat flux for each pebble is generated by the particle-particle conduction, particle-particle radiation, and the particle heating gas convection. Also, the nuclear fission reaction inside the pebbles and from the boundaries. So we solve this equations and by using effective conductive coefficient and use simple model, and also use different kinds of Nusselt number correlations to model convective heat transfer coefficient. And for heat particle radiation, the key point is to calculate the view factor between each particles. Actually, there are three kinds of approaches to calculate the view factor. One is use the Monte Carlo method to predict each kind of the view factor between each pair of particles, and the other the second approach is using empirical fitting correlations, and we use the Monte Carlo method as a fundamental method to generate enough database. We think this database is as accurate as we use this database for to train the to generate neural networks. This picture shows some show the schedule how to train the database. For example, if we give two spheres, then we know all the neighbors around surrounding this pair of particles, and when we know all the location of the particles, we also know how many pebbles are within these two kinds of pebbles. So we just separate the situation into several categories, the two spheres, the three spheres, up to 8 spheres within the two pebbles. And for each category, we use all the neighbors' locations to treat a neural network, and we get after neural training, so we get about 7 kinds of networks, and we use these networks to calculate the view factor between each pair of particles directly. So it can speed up the calculation for view factor fast, and we use this this value in the radiation flux. So this is from this is training data, training results. The X is MC Monte Carlo data. It means it is the accurate, and the Y axis value is the neural network prediction. So we can see for 2 spheres to 6 spheres cases, all the data will restrict into a very narrow region. So we see these training results are acceptable. Although in this case, the data are scattered to a larger range, but if the pair particles has a larger distance to have 6 spheres within them, so the view factor from them is very small. So the scattered region is not impossible. So after use this kind of this is also the particle boundary interaction. So it's similar to the particle boundary interaction for the collision as introduced. For so we just combined all the simulation together. For these slides is also for particle wall interaction. We use empirical correlations to calculate the view factor for particle to wall, and this is coefficients. And we use this correlation coefficients, empirical coefficient, to calculate the heat flux between particle and wall. So after we use these all kinds of models, we just sum up these models into our coded framework. So we just in each iteration, which calculates the heat source, the radiation, conduction, convection, and treat the boundary conditions, and calculate the heat flux from one particle to the other. And for particle radiation, because radiation has a long distance, so when we use local searching, each needs to you use a long distance region. So the mesh grid for local searching should be larger. So we use 2 sets of mesh to one is for collision, one is for heat conduction, and another larger is for particle radiation. And I think the radiation part may cost most of the simulation CPU time. So after we just use finish the coding, we can check what the effective of radiation, the effective conductivity of radiation, and the effective conductivity of conduction between particles. We find in the table beds, the particle conduction has a very low conductivity. It's below than 10 watt per meter per K. But when the temperature reaches to over than 1000 K, the effective conductivity of radiation may go fast, and it's maybe leading maybe the main issue for particle heat conduction. And we just also compare our results with existing empirical correlations. These correlations are mostly based on experimental data. We find the DBS model is best. We just see our simulation results are reliable for actual usage. And we also use existing experiments. This is the HGPU experiment carried out by another group. So the particles are heated inside and cooled outside. When the temperature distribution is steady, we can find the simulation results and experimental measure the results of temperature distribution are very consistent with each other. And if we consider only the particle-particle conduction, the temperature distribution is below this curve, and we just calculate the radiation only. The temperature distribution is higher than the actual temperature distribution. And these two figures show when the heating power is different, and but the consistency between the simulation and the experiments are verified. Also, we compare the computational efficiency between the CPU and CPU with single core, a CPU with 18 cores, and the GPU 2080 type. We can find the overall CPU speedup ratio may increase from 1 to 400. It means when you use the GPU, we can speed up the simulation about 400 times. Then we also this study is already is still ongoing. We just consider the particle heating gas heat transfer, and we calculate the when the pebble the reactor is shut down, and its decay power is about 1.56 megawatts. So we need to know how the decay heat will affect the pebble's temperature distribution. We just show the steady state of temperature distribution inside the pebble beds under different kinds of helium gas pressures from 1 bar to 70 bar, and we can find the highest temperature goes down from more than 800 K to about 430 K. So the last part is the conclusion. So I think we just developed a GPU-DEM numerical model with a heat transfer, and our goal is to realize a full recovery of CFDM simulation of an industrial scale pebble bed. And I think in the next 5 years, I want some PhD students to finish another important task to incorporate a nuclear fission reaction in our code to fully solve the multi-physics inside the reactor core. So it's also very important, but a very difficult task. I needed to solve. Okay, that's all for today. Thank you for listening.
Yes, thanks a lot for Professor Guilan's very good presentations. And now some questions live in their windows, and I'd like to ask you one by one. And the question from Jian Dai, his question is that, and my second, okay, for example, the first question, dear Professor Gui, I have one question about the heat transfer model. I remember that Voronoi tessellation method was used for heat conduction simulation. My question is, if considering long spherical particle shapes, is there any difficulties or challenges? Can you talk more detail about this?
Okay, for if you use Voronoi cells to treat the non-spherical particles, I think you can just use different use different number of phase to cover to replace the non-spherical shape. And it is simple, a geometrical problem to calculate the face-to-face view factors. And when you sum up all the face-to-face view factors, you can get the overall view factor for this non-spherical particle to each surface of the Voronoi face. So I think it's just need some labor for you, but it's not a very difficult problem.
Okay. And from that second question, and my second question is, in your simulation, was there Fourier tessellation calculated in every DEM time step or several time steps? And when particles number is large, for example, 420,000 in your case, what about the time cost used by Valorelli compared with DEM calculations such as contact force calculation or labor searching?
Okay, in fact, we did not use Voronoi cells for industrial scale computation. Because when the particle moves, the Voronoi cells need to be rebuilt, so it's time consuming. So we just abandon this kind of approach and use another kind of using a neural network to calculate the particle, the vector vector between the particles. And we did not use Voronoi cells for dynamic simulation for the pebble flows inside the pebble bed. Okay.
Okay. And the question from Professor Frank Radier, he says that grid model for heat transfer questions. Is it correct that you assume that the temperature is uniform over each particle? To what extent this assimilation affect the results?
Okay, it's a very good question because simply we use just one temperature for a particle, and this is based on the assumption that the conductivity of the particle material is infinity. It can spread the the heat transfer between within the particles. So we may, if we use a uniform temperature for each particle, we may over predict the effective heat conductivity of for the pebble bed. But the other side, we just calculate the radiation heat transfer within a local region. For example, we just calculate the radiation within about 30 diameter distance when the particles are within the 30 diameter distance. So we may cut off a part of radiation heat transfer between long distance particles. So this may underestimate or under predict the pebble bed heat transfer. So this is a balance between this kind of conflict issues. So when we just test a number of cases and to see what kind of distance for radiation is best, and we just call this model as a short distance radiation model. And we find this kind of model is it can consist can fit in the experimental data very well. But we also tried to get get more accurate results when we using a number of measures to cover all the particles and let the let the temperature distribution within the within the pebble are different. It is CPU time consuming work. We can only compute the results within a very short distance or in a very local region. Uh, so we however we also developed another kind of method of subcell particle method. We just I just didn't show this kind of model in this presentation, and in the subcell particle radiation model, it can calculate the finite conductivity of particles material. So we can use the finite conductivity of particle with in the radiation heat flux prediction. And we use this correlation method by some fundamental issues of calculating the packing states of particles and use some data analysis to fit these correlations. We find that these results can be even accurate than the short range radiation model. So I think this kind of method is empirical, but but it can be applicable for real scale simulation of pebble bed. Okay.
Okay, thank you. Yeah, your explanation is very in details. Yeah, and another question from Zhou Quan. I guess Werner tessellation mean the mesh or grid in our model for the pebble flow simulation. The mass information which the particles belong to leads to be updated with each time step in the panel algorithm. This calculation amount is small and can be ignored compared with contact force calculation. I remember that the time was not even as long as the data transfer time between the CPU and the GPU. Yeah, either question or comments, I don't know. Yeah. Is your group, Professor Guilan? Can you answer it
Yes,
or
I
can you?
think he is online. I think he may just say something by himself.
Hello, can you hear
Hello.
me? It's just answer to the second question. It's not a question for my teacher. Okay.
Okay. This is Sochen from his second question. Okay. That's good. So, actually, I have some questions. I just ask some questions for you, and I have one question actually. It's very interesting to your radiation actually considering your work, and I'm wondering, they're doing this radiation in progress. How about the particle properties changing with it? When the radiation happens, the particle density, the size, shape, or surface roughness or rigidity changing with the progress or not? Do you consider this problem, Professor Guilan?
Up to now, we just use thin material of graphite because this is our most interesting material in real engineering. But we can also for other kinds of using application, we can use different kinds of materials, material parameters. Also, I think except the shape, I think shape include the surface roughness is very difficult to concede. The density, size, and rigidity, and I think these issues can be solved very simple. but the shape, it means if we model a non-spherical shape, we need we need to pay more attention to just solve the particle-particle collision searching strategy to solve this problem. It may be consume a lot of CPU time, or we need to another some sophisticated models to solve this problem. And this not it's not considered in our model. Okay.
Yes, you're right. Yes, I know it's very difficult to do this. To do this experiment work. You know, the nuclear actually very dangerous. Yes, it is not easy to conduct this result as the experimental work in laboratories actually. And so, by the way, I'd like to know, you say that all of your work is based on the industry application of the nuclear reactors. So far, do you have some simulation result compared with your reactor? There, some data, some work of their experimental work. Yeah.
We have done some simulation, and we also get the experimental data. For example, the temperature distribution on the walls of the real reactor, but the walls cannot be open to the community. So we just compare by ourselves. So I think for engineering point, we cannot say or say to you how the consistency between the experimental and the simulation results by within for example for the real reactor of HTRPM because I think but maybe some years ago, some years later, maybe the results will be published by our group or by some other group in our institute. But now, I cannot see how the result, the comparison is okay.
Okay. So thank you very much for your presentation. And due to the time near this close of this Kilo's meetings, and thank you thank the Professor Farhan Raja give us a very good presentations. And today we will, yes, I'd like to finish today's presentation, and we like to give you another new presentations in the near future. And please pay attention to our website or the message from our the group. Yeah.